Good morning everyone. Welcome to the lecture series of VLSI technology with the subject code KEC 053. This is the lecture 4. Till now we have studied about the crystal structure, that how the silicon crystal looks like, how that silicon crystal can be used to form the wafers, what are the defects which are present in a silicon wafer, and how that wafer can be polished and further processes are used so that we can use that wafer as a base material for the IC technology. So in this lecture we are going to study about the next layer, that is the epitaxy layer, which is used to grow on the bulk wafer, on the bulk material. Okay, so this epitaxy layer in VLSI technology, in IC technology, there is a need to grow n number of layers on a silicon wafer. So one such layer is known as the epitaxy layer, epitaxial layer. So as per the introduction, the epitaxy layer is a combination of two words, that is epi, which means upon, and taxis, which means ordered. So if you join the two words, epitaxy stands for, its simple meaning is ordered upon. Now what is ordered upon and on what material? So that is the epitaxial layer that is arranged on a bulk silicon crystal or silicon wafer with a minimum thickness. And the difference between the bulk crystal growth and the epitaxial layer is that, suppose we have this wafer, this much wafer, which suppose it has the thickness of 300 microns, and above that we have to grow the epitaxial layer, which has the thickness very much less as compared to the bulk crystal. Now what can be arranged and on what? Epitaxy, in order to grow this thin crystalline layer on the bulk crystalline wafer. So depending upon the choice of the material which is to be grown on the silicon wafer, this epitaxy can be classified into two parts. First one is homoepitaxy and the second one is heteroepitaxy. In case of homoepitaxy, it means that we are using this epitaxial technique to grow the same material over the silicon crystal. For example, we have this silicon crystal, we have this silicon wafer, and we have to grow another silicon layer over this silicon wafer. But the difference is, it may have different doping concentration and may have different resistivity as compared to this silicon wafer. Okay, this is your silicon wafer and this is the grown layer. So in case of homoepitaxy, the same material is used to grow over the silicon crystal, silicon wafer. For example, in case of the fabrication of PNP or NPN BJT transistor, we have the silicon substrate, we have the p-type silicon substrate, and on the top of that we used to grow n-type epitaxial layer. We used to grow this n-type epitaxial layer, and we know that both the materials are made up of silicon. So same material is used this for the epitaxial layer and for the wafer, that is known as homoepitaxy. And this homoepitaxy is a very much simple process. Next is in case of heteroepitaxy. If we have a certain crystal as a substrate or as a bulk material and we want to grow something else on the top of that, that is suppose we have two dissimilar materials. The material of the wafer is differ as the material of the epitaxial layer which is grown on the bulk material. So that will fall under the category of this heteroepitaxy. So one very much common example of this heteroepitaxy is silicon on sapphire. When we have to grow the silicon layer on the sapphire, we know that its common name is aluminium oxide, Al2O3, and it has the hexagonal lattice pattern. This Al2O3 sapphire has the hexagonal lattice pattern, and the silicon, we know that it has a diamond lattice structure. So these two materials have different lattice and we want to grow silicon on the sphere. So that comes under the category of heteroepitaxy. This heteroepitaxy is a very much complicated process and we have to monitor n number of parameters so that your grown epitaxy layer have the desired orientation. So this is the structure of sapphire. This is the structure of sapphire which has the hexagonal. It has the hexagonal structure. And this is the structure of silicon which has the diamond structure. Okay. So we can see from the diagram that both the lattice structures are different. So that comes when we need to grow silicon over the sphere, it comes under heteroepitaxy. Now rules for this heteroepitaxy, it gives us the three cardinal rules which are observed during the heteroepitaxy. The first one is there should be no chemical reaction between the substrate and the epitaxial layer. If some chemical reaction occurs between the substrate and the epitaxial layer, the desired epitaxial layer will not be formed and we cannot go for the further process. Second one is there should be no lattice match, both the lattice should be different. And the third one is that there should be no thermal mismatch. Means the coefficient of the thermal expansion should be matched and there should be no thermal mismatch, we can say. Now out of these three rules, this first rule is very much important. There should be no chemical reaction between the substrate and the epitaxial layer. The lattice mismatch we can tolerate up to certain level. For example, the sapphire and the silicon, there is no lattice matching, right? In the previous diagram we have shown that both the lattice structure of sapphire and silicon are different. Sapphire has a hexagonal crystal structure and the silicon has the diamond like structure, and there is no lattice mismatch, but they can be grown, but the silicon can be grown over the sapphire. So in case of heteroepitaxy, it's a particularly used when we talk about the compound semiconductor technology, when we need to grow some compounds over the semiconductor. For example, aluminium gallium arsenide, we want to grow this aluminium gallium arsenide on gallium arsenide material. This is the example of perfect lattice mismatch. In both the cases, the lattice structure of both the compounds are same. But on the another hand, we have one more example, that is when we want to grow this indium gallium arsenide on gallium arsenide, there will be lattice mismatch. Their lattice structures are different. So in this case, there will be one strained layer grown between the epitaxial layer and the wafer, and that layer will have some properties like how much strain that layer can be used to have, that how much strain that layer can be can tolerate. So in case of homoepitaxy, it is used to grow silicon over the silicon, right? As we have already seen that the homoepitaxy is used to grow the same material. When we want to grow the same material but different doping concentration, different resistivity, we have to vary the doping concentration of silicon. In that case, homoepitaxy is used. So mostly in VLSI technology we use homoepitaxy. However, we want to have some more mostly silicon on silicon with different doping concentration, and but the material will remain same. Doping concentration may differ from wafer to epitaxial layer, but the base material, it will remain same, that is the silicon. Now depending upon what kind of reactions being used during this epitaxy process, whether any reaction is being used or not, this epitaxial system can be classified into three parts. First one is LPE, that is liquid phase epitaxy. Second one is vapor phase epitaxy, and the third one is molecular beam epitaxy. In case of vapor phase epitaxy, VPE and LPE, there are some chemical reactions involved in this, and whereas in case of molecular beam epitaxy, there are no chemical reactions involved in the process. Whereas the MBE is a physical evaporation process, and it is a very much complicated process with a very sophisticated overall system, but the basic essence of MBE is it uses the simple thermal evaporation principle. Now the first one is the liquid phase epitaxy. In case of liquid phase epitaxy, it means that one material should be in the form of liquid. Okay, so first condition is one material should be in the form of liquid. For example, in case of liquid phase epitaxy, suppose we have a solution of gallium arsenide in gallium, and we know that gallium, if we check the condition of gallium at slightly above room temperature, it will be in liquid form. So you can easily dissolve the gallium arsenide in gallium, and if you cool down the solution, the temperature is reduced and the solubility of the solution will be reduced. There will be precipitates of the gallium arsenide. And now if the wafer of gallium arsenides come in contact with the solution as it is being cooled, then the precipitates will be deposited on the bulk crystal, and the deposition can be controlled very carefully. This thing should be kept in mind, that the deposition on the after the deposition of the on the bulk crystal, this deposition process can be controlled. It should be controlled very carefully, so that the orientation of the bulk crystal so that it will take the orientation of the bulk crystal, and we have a single crystal layer on the and a single crystal epitaxial layer on the bulk crystal can be grown. So in essence, this is a liquid phase epitaxy. However, it is not particularly used for silicon, because silicon, it is very much difficult to dissolve the silicon at room temperature or slightly above the room temperature. So for silicon, we always prefer to use a vapor phase epitaxy. Now what is vapor phase epitaxy? In case of vapor phase epitaxy, as the name itself suggests, the material transport must be in the form of vapors. So you have to use some gas reactants in this vapor phase epitaxy, and there is some chemical reaction involved, so that so you have to use some gases or a liquid with a very high vapor pressure, which can be vaporized easily. If you want to use some liquid material, its vapor pressure should be very much high, so that that liquid can be vaporized easily, and that vapors can be deposited on the on a wafer easily. So in chemical vapor deposition CVD, the film is formed on the surface of the substrate by thermal deposition or the reaction of the various gaseous compounds. So as in CVD, the epitaxial layer is formed from the gases, hence it is known as vapor phase epitaxy. So this is the chamber which is used for this vapor phase epitaxy process. In this, your wafers are these are your silicon wafers, which are placed over the graphite susceptor, which is used to support the wafer. We have this RF induction coil, which is used to provide the heating, and this is the reaction chamber. Here we have the outlet, so that extra gases can be sent out. This is known as the quartz tube, and these are the compounds which are used for the reaction, for the epitaxial growth, and these phosphorus, boron and arsenic impurities are used to add the doping to the epitaxial layer. So in this process, the process of chemical vapor deposition grown take place in the reaction chamber as shown in the diagram. This process will be taken place in the reaction chamber, in which a long quartz tube with RF induction coil is wounded. See, it is clear from the diagram that we have some RF induction coil, and the silicon wafers are placed on the graphite rod. This is your graphite rod itself. It is also known as graphite susceptor, which is used to provide the support to the wafer, and then the susceptor is heated by the RF induction to the temperature between 1100 degree C to 1300 degree C, and it is shown from these channels. Some compounds are passed so that doping concentration can be changed. So, 4 important compounds for the wafer phase epitaxy process which in VPE are listed below. First one is silicon tetrachloride, then trichlorosilane, then dichlorosilane and the silane. Out of these 4 compounds, this silicon tetrachloride is most commonly used in the industries, and the temperature for this SiCl4 silicon tetrachloride reaction is controlled between 1150 degree C to 1250 degree C respectively, and for the other compounds we have the lower temperature, and the different gases required for the epitaxial layer formation are allowed in the chamber through the different channels. So, these are the different channels through which different gases can be, different compounds can be passed, and the doping is done by using hydrides of arsenic, boron and phosphorus, and these are arsenides, diborane and phosphine. And in general, the film which is used to grow the epitaxial layer, this epitaxial layer which is used to grow with the help of this VPE process, generally with the width of 1 micrometer per minute. And the advantages of this VPE is nowadays, instead of RF induction coil, heating with quartz halogen lamp is preferred, as it provides more uniform heating, and the doping capability of an epitaxial layer lies in the range of 10 raised to the power 12 to 10 raised to the power 22 atoms per centimeter cube. So, in this lecture we have studied about the need of the epitaxial layer, that what is the need of epitaxial layer, because sometime we have to grow some layer on the silicon wafer, so that another processes can be carried out. So, that layer is known as epitaxial layer. What are the we can classify these epitaxial layer into 2 parts. One is homoepitaxy and the another one is heteroepitaxy. In case of homoepitaxy, when we grow same material over the same material, for example silicon on silicon, it comes under homoepitaxy, and when we used to grow some different material over the silicon or the wafer, it comes under heteroepitaxy. Then what are the various processes which are used to grow this epitaxial layer? First one is liquid phase epitaxy, then vapor phase epitaxy and the molecular beam epitaxy. In case of liquid phase epitaxy we cannot use for the silicon, because the melting point of silicon is we cannot dissolve the silicon very easily. So, for the grown of silicon over silicon we use vapor phase epitaxy. So, in this lecture we studied how the vapor phase epitaxy chamber can be used to grow the epitaxial layer, and what are the compounds which are used for the epitaxial layer, and which are the dopings which are used to change the doping concentration of epitaxial layer and the resistivity of the epitaxial layer. And finally, the advantages of VPE, and these days we can use the halogen lamps also, so that they can provide the uniform heating, and the doping capability of epitaxial layer which lies between the range of 10 raised to the power 10 to 10 raised to the power 22 atoms per centimeter cube. So, in the next class we'll going to study about molecular beam epitaxy, that how the molecular beam epitaxy is used to grow the epitaxial layer. Thank you so much.